Welcome to Ask and Learn.
In this problem, we have to find out the value of the y equivalent across these two given points, right? So we have to find out the equivalent impedance. So there are some important points before starting this problem. So let's suppose we have two different impedances, two different impedances like value of Z1 and Z2, and these are connected in series. So we have to find out the equivalent impedance. Let's suppose this is the equivalent is Z equivalent, and the value of Z equivalent is can be written as Z1 plus Z2. This is the point number one. And the second point, if we are going to find out the Z equivalent in the parallel sequence, so if they are in the parallel combination, so the value of Z equivalent for parallel combination can be written as, let's suppose the value of Z equivalent is Zeq. So this will become 1 upon Z equivalent is equal to 1 upon Z1 plus 1 upon Z2. These 2 points should be taken care of before starting the such problems, right? So as you can see, these two and these two are in series. So as we have to find out the Z equivalent, let's suppose we are only interested to find out the Z equivalent of these two, similarly these two. So we will simply get the value of their Z equivalent by simply adding both of them according to this point, right? So let's suppose I am going to redraw the circuit. So the equivalent circuit will be like something like this. This is, let's suppose this is Z1, and this is Z2. This is a Z1, this is a Z2, right? So, and another one is minus 4J, this is still remaining, which is this is a Z2, and this is minus 4J capacitance. This is minus 4J, and the value of Z1 is, the value of Z1 from the above circuit can be written as this 3 plus 1. So this will become 3 plus 1J ohm. 3 plus 1J ohm, right? And then another one, the value of Z2 is 5 minus 2J. So we can simply write it as Z2 is equal to 5 minus 2J ohm. Now if you look at this circuit, these three are in series combination. So we can simply write the, as it is given in the problem that the equivalent impedance will be Y equivalent. So we can write it as 1 upon Y equivalent is equal to 1 upon Z1 plus 1 upon Z2 plus 1 upon minus 4J, because all are in the parallel combination, right? So let's put the value over here. So what you will get is 1 upon Y equivalent, 1 upon Y equivalent, and the value of Z1, the value of Z1 is 3 plus 1J. So this will become 3 plus 1J. Similarly, the value of Z2 is 5 minus 2J. So this will become 1 upon 5 minus 2J. And this is already given minus 4J. So this will become 1 upon minus 4J. Now we have to simplify it. So let's suppose I am going to simplify it. This will become 1 upon Y equivalent, and just multiply the conjugate by numerator and denominator both. So you will get 3 minus J over 9, which is the square of 3, and 1. Similarly, here you will get 5 plus 2J upon the square of 5, which is 25, and then square of 2, which is 4. And similarly, if you will do the same thing over here, you will get J by 4, right? So the value of 1 by Y equivalent will be, if you further simplify, you will get 3 minus J by 10 plus 5 plus 2J by 29 plus j by 4, right? Now just we have to just simplify it. So after simplification, what you will get is 1 upon y equivalent by just simplify with the help of by taking LCM of denominator and then further calculation. You will get it as 419 minus 18j by 580, and this is the value of 1 by y equivalent, and we are interested for the y equivalent. So just reverse it. So what you will get is the y equivalent will be 580 by 490 minus 18. Now what you need to do is just multiply with the conjugate of this denominator. So what you will get is 580 into 490 plus conjugate is plus 18j, and this will become the square of this term, 419 square plus square of 18. This will be 18 square, right? The value of y equivalent will be, if you simplify the calculator, you will get is y equivalent is equal to 1.38 plus 0.059 j. So this is the final answer. So this is our y equivalent for the given circuit.